Sabyasachi Mukherjee from Tata Institute of Fundamental Research, Mumbai. He did his PhD from Jacobs University, Bremen, and his research interest is in the field of conformal dynamics. Today, he will introduce a correspondence between two different areas of conformal dynamics, namely the action of Kleinian groups and the dynamics of rational maps. So let me invite Professor Sabyasachi Mukherjee.
All right, thank you. Thanks, Divakaran, for the introduction, and thank you, the organizers, for letting me speak here. It's a great opportunity. It's a great privilege to be speaking in this Math Fest, which is in many ways sort of a first initiative of its kind. So it's a great pleasure, and I hope that this talk will help at least some people. Okay, so I'm supposed to give a survey talk on some of my research, and I decided to talk about a link between rational dynamics and Kleinian groups because it sort of touches upon various areas of conformal dynamics. And obviously, while preparing the talk, I had to make a choice of topics, and this is neither going to be a talk purely on complex dynamics, nor going to be a talk on three-manifold Kleinian groups. I had to choose topics that are close to my own research interest. And again, it's not going to be a comprehensive sort of study of the dictionary between the two subjects. I just had to choose some topics on which I have something to say about. Okay, so let me start. So the basic objects that we study in conformal dynamics are rational maps on the Riemann sphere and Kleinian groups. So a rational map on a Riemann sphere is simply the ratio of two polynomials. It's the quotient of two polynomials, and the degree of the map is the maximum degree of P and Q. And this degree is both the algebraic degree and the topological degree. Now, since we are talking about dynamics of a rational map, what we are more interested in, or rather primarily interested in, is the sort of the long-term behavior of orbits under a rational map. What that means is you take a point on the Riemann sphere and you keep applying the map R over and over again, and you want to see what's happening with the point in this orbit. So you can study that topologically, measure theoretically, or statistically, or analytically, and so on. On the other hand, so keep in mind that for all rational maps in the talk are going to have degree at least 2. So we are not going to be interested in the dynamics of Mobius transformations, which makes the dynamics of rational maps more interesting because they have more interesting in the sense it's much more interesting than the dynamics of Mobius maps, of a single Mobius map, because of the existence of critical points of a rational map. On the other hand, a Kleinian group is just a discrete subgroup of PSL2C. So it's now PSL2C can be viewed both as a group of conformal automorphisms on C hat. We know Mobius maps act as conformal automorphisms of C hat. But they also have a natural extension to H3, so the three-dimensional hyperbolic space. So you can think of the three-dimensional hyperbolic space as a ball, and the Riemann sphere is the boundary. So the action of any Mobius map on the boundary Riemann sphere also naturally extends as a hyperbolic isometry to H3. So the space H3 has a natural metric on it, the hyperbolic metric, and actions of Mobius transformations are isometries in this metric. So this brings in the perspective of geometry, of hyperbolic geometry in this picture. Okay, now, in order to study these things dynamically, we have to first split our dynamical plane, which is the Riemann sphere, into two naturally sort of invariant subsets. Now, for a rational maps, the subsets are called the Julia set and the Fatou set. So a Fatou set of a rational map is in some sense the region where the dynamics is easier to understand or easier to describe. So it's basically the set of all points, the largest open set on which the iterates, because that's what we're interested in, form a normal family. What this means is that the iterates are equicontinuous in the sense that if 2 points are close to begin with, then under the iterates of the map, they'll stay close forever. So the dynamics is not too chaotic. The journey of 2 points that start together is pretty close to each other. They stay close forever. And the complement of this thing is a Julia set, which is a closed set. So the Fatou set by definition is open, and the Julia set is a compact subset of the Riemann sphere. On the Julia set, the dynamics is chaotic. So I'll come to that later. And the analog of these things in the world of Kleinian groups is the domain of discontinuity, which corresponds to the Fatou set. It's again the same thing. This is where the group acts properly discontinuously or form a normal family. This is where the dynamics is easy to describe. Now, the proper discontinuity allows you to take, to find a fundamental domain and find a quotient of the region of discontinuity by the group. And that's how sort of more topological things come in. And on the other hand, the complement of the domain of discontinuity is the limit set. This is what corresponds to the Julia set of a rational map. So the vague parallel is that a rational map corresponds to a Kleinian group philosophically. The Fatou set corresponds to the domain of discontinuity. The Julia set corresponds to the limit set. Now, observe that in the group setting, the action of the Kleinian group also extends to H3. Hence, we could actually construct a 3 manifold out of this action. You can take the quotient of the hyperbolic 3 space, union the domain of discontinuity, because this is where the action is properly discontinuous. If you take the quotient of this thing by the group gamma, what you get is a hyperbolic 3 manifold with boundary. And I'm calling it the conformal boundary because there is a conformal structure on it, because this set lies on the Riemann spheres. It has a natural complex structure. So the quotient, which is the boundary, also has a natural structure as Riemann surfaces. So in the group setting, there is this natural three-dimensional object associated to a Kleinian group. However, for a rational map, there is no such obvious thing. There have been attempts to associate a 3-dimensional object to a rational map, but it's much less clear, and I'll not say anything about that. So that's one example, or rather one instant where there is some sort of a mismatch. In the group setting, you do have a 3-dimensional analog. In the rational map setting, there is nothing as such. Okay, so with these definitions in mind, let me try to substantiate the statement that the limits analog of the Julia set, at least philosophically. So the pictures you see, so a lot of my talk will be in pictures. I'll try to avoid definitions and so on. So this is the limit set of a certain group. It's a Cantor set, which is not so easy to see, but it is a Cantor set. And the same thing here, this is the Julia set of a rational map. And they look pretty similar. Again, here, this is the limit set of a certain group, and this is the Julia set of a rational map. As you can see, they're topologically indistinguishable. They're both homeomorphic to the classical Sierpinski carpet. And so part of what people observed, something that Fatou observed already in the 1920s without having access to any of these pictures, was that there is this similarity between these two classes of objects. It cannot be purely coincidental. There has to be a synthetic theory for these things. However, there is no grand synthetic theory to explain everything. There are bits and pieces. So some of the mathematical similarities beyond pictures is that both the Julia set of a rational map or the limit set of a Kleinian group, they're either the entire sphere or they're nowhere dense. So in these pictures, they're nowhere dense. There's no point drawing a picture of an entire sphere, but there are examples of limit sets that are entire sphere and of Julia sets that are entire sphere. So those are very complicated dynamics. The dynamics is chaotic on the whole sphere. Also, a dynamical similarity between the two things is that the Julia set is the closure of periodic points. Now, this suggests something. This suggests that if you take any point on the Julia set, there is a nearby point that is periodic. So it comes back to itself. But that point itself that you started off with, that has nothing to do with periodicity. So that can have a very different dynamics. So the idea is that on the Julia set, if you pick 2 points that are close to each other, their dynamics under the rational map can vastly vary. And on the group side, you have a similar thing. The closure of the fixed points of all the group elements is the limit set. So these are some elementary similarities between these two things. Now, moving on to sort of more deeper or more serious mathematical similarities, I want to actually introduce one notion. This is probably going to be the only kind of formal definition in the talk. And this is the notion of a quasi-conformal map. This is what revolutionized the field of complex dynamics and also played a key role in the study of Kleinian groups. So what is a quasi-conformal map? So roughly speaking, a conformal map is something that's a conformal map is something that preserves angles. And if you look at the tangent plane, then it sends, basically, if you take a conformal map, then at the level of tangent planes, the derivative of the map sends circles to circles. That's what the Cauchy-Riemann equation basically tells you. That's all it tells you. It sends circles to circles at the level of tangent spaces. On the other hand, a quasi-conformal map is something that has some amount of low regularity so that you can talk about the derivative. And I'll not explain what low regularity means. I certainly don't want to assume that the map is smooth, C1, or anything of that sort. Low regularity roughly means that it's differentiable almost everywhere and so on. So you can actually talk about the derivative at almost every point. And when you look at the tangent space, the derivative is a linear map. So clearly, it's going to pull back a unit circle here, for instance, in this tangent plane, to an ellipse in this tangent plane. The quasi-conformality condition is that while a conformal map pulls back circles to circles, so round circles to round circles, a quasi-conformal map will pull back a round circle to an ellipse that is not too stretched, meaning there's a uniform bound on how much the preimage of a circle can be stretched. So how much the preimage ellipse is stretched. So that is the notion of a quasi-conformal map. Now, from the definition, it sounds like a simple-minded generalization of conformal maps, but it turns out to be an extremely powerful tool in all of conformal dynamics. And the reason is that conformal maps are way too rigid. You know, from the identity theorem, you cannot piece together two conformal maps. If it's defined somewhere, it's basically defined everywhere by the identity theorem. On the other hand, a quasi-conformal map is precisely what allows you to do these kind of gluing and surgery constructions. So if you want a desired dynamics, or you want a desired behavior of a map here and some other kind of behavior over there, a quasi-conformal map has the right kind of flexibility to allow you to do that. So that's the moral thing one should keep in mind. And the main theorem that makes quasi-conformal maps so powerful is the following measurable Riemann mapping theorem, which basically says that if you take an ellipse field on, well, on let's say the Riemann sphere, which is something I've drawn here, what that means is that you just associate an ellipse, and associating an ellipse just means telling me what the eccentricity of the ellipse is and the direction of the major axis. So if you tell me the major axis of the ellipse, the direction of the major axis of the ellipse, so for instance here, and if you tell me the ratio of the major and minor axis, I can draw the ellipse up to stretching. And if I do that at all points, or let's say almost every points, what I get is an ellipse field. And keep in mind that the ellipse field actually lives on the tangent bundle. So it's on the tangent bundle, but not at every point. The association of an ellipse is at almost every tangent planes. So, and what I require is that the ellipse field is essentially bounded, which is exactly what I said earlier. It means that the ratio of the major axis to the minor axis or if you take the minor axis over the major axis, that's a number less than 1. But I'm not allowing this ratio to go to 1, to go arbitrarily close to 1. So there's a uniform bound on how much the ellipses are stretched. And if you have such an essentially bounded ellipse field, then there exists a quasi-conformal map that, so there exists an orientation preserving homeomorphism with the right kind of regularity that pulls back the usual circle field to the given ellipse field. And I cannot overstate the importance of this result. This is a fundamental theorem in conformal dynamics and much of complex analysis too. Now, just to give you an idea of why this is important, suppose you start with a rational map or a group, and you want to deform the group. So in dynamics and many other fields, deformations of objects are important, and you want to have a good control theory of how you can deform objects. Now, how can you deform a rational map? Well, one way of deforming a rational map or a group is to just naively perturb the coefficients a little bit. But that is bad, because when you perturb the coefficients a little bit, then you have basically no control over the dynamics of the new map, of the perturbed map. So what if you want to perturb a map or deform a map or a group, preserving some of the dynamical properties? This is what the measurable Riemann mapping theorem allows you to do. You start off with, if you can construct an essentially bounded measurable ellipse field that is invariant under the rational map, in the sense that if you have an ellipse here at the point Z, and this is the point RZ, then then D of R pulls back this ellipse to that ellipse. In the same way for groups, if you have a group element that takes this point to that point, then the ellipse here pulls back to the ellipse there. So if you have this invariance property, then it's easy to check that the measurable Riemann mapping theorem gives you a map in this direction, which pulls back the circle field to the given ellipse field. And the conjugate of R or the group gamma under this map is again, and this is very important, is again going to be either a rational map or a Kleinian group. So what is so special about this construction? What is special is that phi itself is not a conformal map. Phi itself is a map of a very low regularity. When you're conjugating a rational map R or a group gamma by phi, there's no a priori reason to expect that this conjugated object is also going to be a holomorphic object or a bunch of Mobius maps. But that is guaranteed by the invariance of the ellipse field here. What happens is that the conjugated dynamics, the conjugated map, preserves the circle field, meaning it pulls back the circle field to the circle field. And that's enough to conclude with some more details here. There's something called Weil's lemma that needs to be invoked here. But with some details, something that I'm pushing under the carpet, one can actually show that the conjugated objects are again rational maps or Kleinian groups. So this existence of quasi-conformal maps, or the abundance of quasi-conformal maps, allows us to deform rational maps and groups. Okay, so this is the most technical slide of this talk. But this is something I would like people to sort of take away from the talk, this particular technique. All right, now what are these good for? So I just explained that it allows you to deform maps or deform groups. And these ideas have been used to prove the following two theorems, which is one of the main reasons why the dictionary was conjectured by Sullivan. So on one side, recall that for a group, for a Kleinian group, we have the domain of discontinuity where the dynamics is tame in some sense. It's a stable region, and we want to understand what the quotient is. The Alfor's finiteness theorem basically tells us that if I have a finitely generated Kleinian groups, all the groups in this talk are going to be finitely generated. If I have a finitely generated Kleinian group, then this quotient of the domain of discontinuity by the Kleinian group gamma is a finite union of Riemann surfaces of finite type. So this is a very strong result that basically tells you that if you have some component of the domain of discontinuity of omega of gamma, then there is some group element that fixes it, that leaves it invariant. So you can take a quotient and it's going to be a Riemann surface of finite type. And there are only finitely many such quotient surfaces that you get. So understanding the dynamics of gamma on the domain of discontinuity boils down to understanding finitely many Riemann surfaces, essentially. And the analog of this theorem for rational maps is the following. Well, so I'm just replacing the domain of discontinuity by a Fatou set, and I'm taking a component of the Fatou set. And the statement is that there are no wandering domains, meaning if you start with any component of the Fatou set, under the iteration, it will not keep wandering around throughout the space. At some point, it will come back. So maybe it won't come back to itself. That's why I'm saying it's eventually periodic. So it may happen that a component goes to the next one, goes to the next one, and so on, and then comes back to itself. So eventually it will fall into a cycle. And again, these two theorems, if you think about them a little bit, they are actually of the same flavor, and they're proved using more or less the same kind of arguments. You start with a map or a group, and you quasi-conformally deform it, and you use the finite dimensionality of the deformation spaces. So keep in mind that the rational map of a given degree is a finite dimensional space, or the space of all rational maps of a given degree is a finite dimensional space. And the same thing is true if you take a finitely generated Kleinian group. So the existence of infiniteness or wandering property in the dynamics would contradict the finite dimensionality of the deformation space. Okay, now, so that's a fundamental, these are fundamental theorems. It tells you that the dynamics on the domain of discontinuity is tame and the dynamics on the Fatou set is tame. And these allow you to connect the dynamics, the dynamical properties of rational maps and groups to Teichmüller spaces of surfaces. How do Teichmüller spaces of surfaces come in? Well, here you can clearly see there are finitely many Riemann surfaces of finite type in the quotient. Here, it's a little harder to explain, so I'll not get into it, but you can still talk about when something is periodic, you can talk about a fundamental domain, and you can take the quotient of the fundamental domain by the map, and that's what gives rise to surfaces again. Okay, and there are also other parallels. So there are three major theorems of Thurston, and I'll not say much about these. So one of them classifies homeomorphisms of compact orientable surfaces, which tells you that if you start with a homeomorphism of a compact orientable surface, then in its mapping class, meaning there is some map in its isotopic class that is either, well, there are three possibilities. Let me not list the possibilities, but it describes what can happen with those maps. And there's a similar theorem that Thurston proves for rational maps. He characterized arbitrary branched covers of the Riemann sphere. Well, post-critical, well, there's some more details here, but I'm just hiding some details, but he gave a classification of which branched covers of S2 can be realized as rational maps. And the other theorem, which is the hyperbolization theorem for three manifolds, which gives a sufficient condition for a three manifold to have a hyperbolic metric on it. All of these results are related, at least the proof techniques have some parallels. And the main goal of all these results essentially is to, you start with a topological object, and when can you promote this topological object to a conformal object? That's the main idea of all these theorems. So that's another parallel amongst these two fields. All right, now moving on to limit sets and Julia sets, now that we have some ideas about Fatou sets. So the existence of the critical points of a rational map makes the dynamics of a rational map on the Julia set much harder to understand. For instance, it's known that, for a Kleinian group, if the limit set is connected, then it's also locally connected. And that allows you to study the thing as sometimes as a quotient of a circle. On the other hand, there are known Julia sets that are connected but are not locally connected. On the measure theoretic side, Kleinian limit sets always have zero area, but there are Julia sets that have positive area, which make it harder to understand. And there's a big open question in the field. So you see, here I was talking about invariant ellipse fields. Now the point is, it's easy to imagine that there is an invariant ellipse field supported on an open set, on the Fatou set, or on the Fatou set. Whereas the Julia set is nowhere dense, but it can still have positive area. So the big open question in complex dynamics is, can there be a rational Julia set that supports a non-trivial invariant ellipse field? Meaning, can I quasi-conformally deform a rational map such that this deformation is supported only on the Julia set, the region where we do not understand the dynamics much? And if there are such invariant ellipse fields supported on the Julia set, that would be very difficult. That would lead to so much more complexity in understanding of parameter spaces. But it's still open, and it's a big open question. Okay, so let me say try to at least come to the parameter space side of things. So quick definition, a Fuchsian group is a special kind of a Kleinian group. It's a discrete subgroup of PSL2R. In my talk, I'm gonna normalize so that they are automorphisms of the disk, not of the upper half plane. And the limit set is actually the circle. So for instance, it could happen that this is the limit set of a given Fuchsian group, and the domain of discontinuity has these two components. And so clearly the quotient of the domain of discontinuity under the group will be a pair of Riemann surfaces coming from the two quotients. They are actually homeomorphic, maybe this. I'll call one of them the top surface, the other one the bottom surface. And in order to find a nice class of maps that contain this Fuchsian group, or a class of groups rather, a deformation space for these groups, Beers constructed what's now known as the Beer slice. So it's the set of all quasi-conformal deformations of a Fuchsian group where you change the quasi-conformal or the conformal type of the bottom surface S minus, but you do not change the conformal type on S plus. So you keep one side fixed and change the conformal type or the conformal structure on the bottom surface S minus. Now, if you are familiar with the concept of Teichmuller spaces of surfaces, then you see immediately that this basically means, given the measurable Riemann mapping theorem, it basically tells you that when you're not perturbing or not changing the dynamics upstairs on the top surface and changing the conformal structure on the bottom surface S minus, and you're allowed to change sort of range over all possible complex structures, this gives you an analytic realization of the Teichmuller space. So the Teichmuller space, which is a space of complex structures up to isotopy, can be realized as a space of marked groups, which is the Beer slice. Now, why did I mention the Beer slice? Well, the point is that every group on the Beer slice closure, so first thing, the Beer slice can be compactified in a suitable representation space, and every group in the closure of a Beer slice has an invariant component. The domain of discontinuity has an invariant component. For instance, here is a picture of the limit set of some group on a Beer slice closure. And you see that this white region, this is an invariant component. Similarly, the analog in the dictionary is the basin of infinity of a polynomial. So what I have drawn on the right, or what I have shown on the right, is the Julia set of a polynomial. And every polynomial has an attracting fixed point at infinity. You can imagine if you take a point and if the degree of the polynomial is greater than 1, then under iteration, if you start off with a point that's close to infinity, then under iteration, it flies off to infinity. And this orange region here is precisely the set of all points that diverge to or converge to infinity. So in that sense, groups on a Beer slice closure and polynomials correspond. There's a vague analog between them. They all have an invariant component. Now, one interesting connection between these two parameter spaces, like complex polynomials and Beer slice closures, is the following. So in the 90s, Thurston and Kerckhoff proved that if you take two different Beer slices, now what do I mean by two different Beer slices? Well, if you go back to the definition, here you are not changing the dynamics upstairs, you're only changing, but you're changing the dynamics, or not the, you're not changing the conformal structure upstairs, you're changing the conformal structure downstairs. So meaning here you are fixing the conformal structure. You could fix it to be something, or you could fix it to be something else. So depending on how you are fixing the top conformal structure, you'll get various Beer slices and various Beer slice closures. While there's a natural biholomorphism between two different Beer slices, this biholomorphism almost never extends continuously to the boundaries. And there's a similar phenomena in complex polynomial parameter spaces. There are naturally what I call straightening maps. There are naturally defined dynamical maps between polynomial parameter spaces that are biholomorphic when restricted to sort of the interior of the parameter space. And I'll not say more than that, what I mean by interior of a parameter space, but restricted to the nice part, they are biholomorphisms, but they do not extend continuously to the boundary. And well, the proofs of these two facts are different in some sense. The techniques are very different. So it'll be quite interesting to see if there is a unified framework to explain these parallel phenomena. All right, now, once we have the theory of quasi-conformal maps and Fuchsian groups, well, so recall that the way we defined the burst slice, what was it? Basically, we started with a Fuchsian group. We had two surfaces, the top and the bottom. We fixed the structure on the top and we changed the one at the bottom. That's what gave us the burst slice. Now, how about we change both? What if we change the complex structures on the top surface as well as the complex structures on the bottom surface? And if we do that, this is what gives rise to a general quasi-Fuchsian group. So an arbitrary quasi-conformal deformation in general corresponds to QC deformations of both the surfaces, the top and the bottom. And there is a theorem of Burst, celebrated theorem from the 60s called the Simultaneous uniformization theorem, which says that if you freely change the complex structures on the top surface and the bottom surface, so roughly that means you're arranging over all complex structures here and all complex structures there. So you would expect that what you get is a product of two copies of the Teichmüller space, corresponding to the top and the bottom. And that is true. The space of all QC deformations is really just the product of two copies of the Teichmüller space. Now, when you have such a deformation space, it's always interesting to see what happens if you take a sequence that degenerates. So what happens if you take a sequence of quasi-Fuchsian groups that leave all compact sets? Is there something they converge to in the boundary? Is there some sort of a subsequential limit of these guys? And this is the content of Thurston's double limit theorem. It says that under suitable conditions, not very strong, an arbitrary sequence of quasi-Fuchsian groups, I'm assuming that the sequence is degenerating, meaning it's leaving the space of quasi-Fuchsian groups, has a subsequence that converges algebraically, meaning generator-wise. So if you have a sequence generated by some number of, a sequence of group with its marked generators, then the generators of these sequences of groups converge to generators of the limiting group. Now, if you think about it one more time, what does it mean to degenerate? It means that you take a sequence of quasi-Fuchsian groups gamma n, and essentially you're changing the top surface as well as the bottom surface. And if you just change the bottom and not the top, then what you get is a group on the burst slice closure. Same thing, if you just change the top and not the bottom, then again, what you get is a group on the burst slice closure. So when you simultaneously change them and go to a limit, what you get is, like, in some sense, two groups on the burst closure or the burst boundary mated in some sense. So this is the notion of mating coming from the double limit theorem. So where something on the boundary of the quasi-Fuchsian deformation space is rather complicated, but sometimes if you understand how you got it, then you can sort of decompose it in terms of two simpler objects. And there is an analogous construction for two complex polynomials. So complex polynomials, as I said, are easier to dynamically describe than general complex rational maps. But if you can obtain a complex rational map as the mating of two polynomials, it would be a great thing. Then you can basically study the dynamics of the rational map in terms of the two polynomials. And of course, I don't have the time to define what this means for what it means to mate two polynomials. So I'll just show a movie. So we start with two Julia sets, both of which are actually nowhere dense. Well, they're just dendrites. And what you see is that they're being mated, meaning they are coming close to each other and somehow they're being identified. And in the limit, what you get is a Julia set that is the whole sphere. So this is an example of a rational map which has a full sphere Julia set. So rather difficult to describe its dynamics, but if you can write it as sort of the mating of two polynomials, then it becomes much easier to understand the dynamics in terms of these two components, these two polynomial components. All right, so that's all good. Maybe in the last 10-15 minutes, I should mention some recent work in the dictionary. So keep in mind that most of the stuffs that I mentioned in the previous two slides, these are philosophical. I'm not claiming that Baire slices correspond to polynomial parameter spaces, or the notion of mating of groups exactly corresponds to the notion of mating in polynomial spaces. It's a vague analogy, and the question is, in some cases, can you actually implement this analogy and use the dictionary? Can you make a perfect connection between two classes of objects? And that's what I want to describe in the remaining few minutes. So this is joint work with the people listed here. Okay, so let me just first try to explain this line here. So here we are not looking at Kleinian groups per se. We are basically looking at all conformal and anti-conformal automorphisms on the Riemann sphere. So these are going to be reflection groups. These are the simplest kind of groups that you can talk about. Well, at least to generate them, it's quite simple. If you have a circle packing, well, so what's a contact graph? Let me just mention that every circle packing in the plane has a so-called contact graph. So what does it mean? You associate a vertex to every disk, and you connect two disks exactly when the corresponding disks touch, right? So the red thing I have drawn is the contact graph of the blue circle packing. Now, when you have a circle packing, and this is a bijective correspondence, every connected planar simple graph can be realized as the contact graph of some circle packing. And here I'm talking about a finite circle packing. But when you have a finite circle packing, you can talk about the group of reflections generated by the circles in this circle packing. For instance, these blue circles here. This will give rise to a reflection group, which is basically at the index, which has an index to Kleinian subgroup, but let me just think about the reflection group itself. And it turns out that the reflection group has a connected limit set if and only if the contact graph is too connected. I'll not say much about that. The point is, this is the important part of the dictionary. The space of all reflection groups constructed this way from circle packings with connected limit sets bijectively correspond to a certain space of anti-holomorphic rational maps. Anti-holomorphic because on this side I have reflection groups, so I should allow orientation reversing objects on the other side too. The theorem says that every reflection group with a connected limit set arising from a circle packing has a corresponding rational map, anti-holomorphic rational map, all of whose critical points are fixed. Now, how do they correspond? The basic idea is that the limit set of the rational map and the Julia set of the corresponding group are homeomorphic. And this homeomorphism also preserves certain dynamical properties. To explain, let me just show a picture. So here is a certain contact graph, and it's realized as the gray circle packing. As you can see, there are 4 circles, and they touch exactly as they are mandated by the corresponding contact graph. And this thing is the limit set. The thing in white is the limit set. And here is anti-rational map, here in this case an anti-holomorphic polynomial, whose Julia set is homeomorphic to the limit set of this guy. And this is not just a homeomorphism. The homeomorphism is constructed in a dynamical sense, but I'll not say much about that. Now, once you have this, and this is a bijection, so every connected limit set of a reflection group coming from a circle packing has a corresponding critically fixed anti-rational map, and vice versa. Okay, now what is this good for? What can I do? Well, so with this new entry in the dictionary, can I explain some of the phenomena of Baire slice closure corresponding to polynomials, or double limits corresponding to matings, and so on? And turns out that this is true, so we can do both. If I choose a group that's, again, a reflection group coming from a circle packing, that's on the closure of an ideal polygon reflection group that actually corresponds to a polynomial. So here's the example, basically. You can see that this group really is on the boundary of the Baire slice of a certain Fuchsian reflection group. What I mean is the following. You see this group, or rather this contact graph, Its circle packing is shown on the middle picture, these 4 gray circles. Now you could start with something like this. Instead of having 4 circles with the desired tangency shown in the contact graph, you just start with 4 circles that look like this. So it's just pairwise touching. And if I draw the picture correctly, then the limit set will actually be a circle. I have not drawn it correctly. I had to draw 4 circles of the same radii. And then the limit set is actually a circle, and this is a Fuchsian reflection group. And well, just like Fuchsian groups, they also have a top surface and a bottom surface. And in this case, they are both punctured spheres. And how do you get from this Fuchsian group to that group? Well, basically you observe that all you need to do is pinch a curve here. This is a 4 times punctured sphere, and this is a simple closed curve, and quasi-conformal deformations basically allow you to pinch curves. And pinching this curve will mean that these 2 guys come together and touch. And you're doing nothing to the top group, the top surface rather. So the top surface is fixed, the bottom surface is quasi-conformally changed, and it goes to a limit, and this is how this group is produced. So this is a group on the burst slice closure of the ideal polygon group, and it corresponds to a polynomial. Going one step further, why don't we look at this contact graph? Well, this contact graph is not so different from the previous contact graph, actually. The blue edges here correspond to the blue edges there. The only difference is that in the previous one, there was an edge connecting these guys and no edge connecting those guys. Here, I also have that. What this means is that in order to get a circle packing, so this is basically, this particular contact graph is generated by 4 circles, namely these. Well, there's a red circle here, a red circle there, a red circle there, and a red circle inside. Now, how do I get this particular group, starting with the Fuchsian reflection group of an ideal quadrilateral reflection group? Well, you observe that in the previous case, you only pinched one loop, namely this guy, and did nothing to the top surface. Here, you are going to pinch 2 loops, one on the top surface, one on the bottom surface, and you're going to do that simultaneously. And again, the double limit theorem essentially tells you that you can do that, and in the limit, you will have a group, which is this particular reflection group. On the polynomial side, this means something. This means that this particular rational map is a mating of this polynomial with itself. So here is an example. So of course, I'm pushing a lot of details under the carpet, but roughly what I'm trying to say or trying to convey is that here is a precise dictionary between groups on the burst slice closure and anti-holomorphic polynomials, and groups on the quasi-Fuchsian closure and rational maps that are mating in the setting of reflection groups. There's one more thing that I should mention, that there's a celebrated theorem, there's a very sort of important theorem by Thurston called the compactness theorem. And without defining any terms, let me just mention that compactness theorems or boundedness theorems are very important in deformation, in the study of deformation spaces. And the theorem of Thurston that I'm looking at right here, it says that if the 3 manifold satisfies a certain property, then the quasi-conformal deformation space is pre-compact in some bigger space. And the property is of being acylindrical, which just means that it does not contain any essential cylinder. In the 3 manifold does not contain an essential cylinder, whatever that means. Now, what we see here, so now we want to basically explore the dictionary. Recall that we have this correspondence between reflection groups and rational maps. So one thing that the dictionary does for us, it produces problems. It gives us it's sort of a source of problems. If you have a result that holds in the reflection group setting, you ask whether the same thing would hold in the other side, whether the results translate. And the translation that we are looking at here is the following. So suppose that you have a reflection group whose 3 manifold is acylindrical. And it turns out this is where there's a simple way to characterize, but let me not get there. Suppose that suppose that there is a reflection group whose three-manifold is acylindrical. So its quasi-conformal deformation space is pre-compact. So the question is, what about the corresponding rational map? So here is a graph. Here is a reflection group. This is an acylindrical example. So this has a bounded deformation space. The question is, will the corresponding rational map also have a bounded deformation space? And that is something we proved, that the Thurston's compactness theorem actually holds for this class of anti-rational maps as well. So this is an example where you find a dictionary between two classes of objects, you take a result that holds in one setting and you ask whether it holds in the other. And sometimes you can do that. Sort of to conclude, let me mention a few problems that are motivated by this dictionary. So as I said, the main result here is that you have a correspondence between reflection groups and anti-holomorphic rational maps of a suitable kind, such that the limit and the Julia sets are homeomorphic, as I have shown in this picture or that picture or this picture. They're all homeomorphic, the Julia and the limit sets. And our proof basically is an explanation of this thing on the Riemann sphere. So all the tools are on the Riemann sphere. But the question is there an intrinsic three-dimensional explanation for this similarity? That would be a really good thing to understand. Another question is that, so if you are familiar with quasi-symmetric maps and quasi-conformal maps, you would know that this limit set here and this Julia set there, although they're homeomorphic, they're actually not quasi-conformally equivalent, meaning there is no quasi-conformal homeomorphism that takes this limit set to that Julia set. And the reason is that, well, it's a pretty easy thing to see. Here you see a cusp. There's a zero angle axis towards this point here, but there's a positive angle axis to that point there. So there cannot be, quasi-conformal maps preserve cusps. They cannot open up cusps. So this homeomorphism between these two things is not quasi-conformal. And of course, the picture suggests that. Can I somehow prove that? Like, just like when you want to prove that two spaces are not homeomorphic, you, for instance, sometimes you compute their fundamental groups or homology groups and try to prove that they are really not homeomorphic. There's a similar notion for quasi-conformal equivalence, which is called a quasi-symmetry group. This is actually a similar invariant of two fractals that are quasi-conformally homeomorphic. So if two things are quasi-conformally homeomorphic, they will have the same or isomorphic quasi-symmetric groups. So it would be interesting to compute the quasi-symmetric groups of these classes of fractals and see whether the quasi-symmetric group indeed distinguishes these two objects. And finally, let me also state that these groups are particularly special, in particular the Kleinian gasket group and these kind of groups that are gaskets, whose limit sets are gaskets. They have certain number theoretic properties, and there are a lot of equidistribution results, ergodic properties known about these limit sets. It would be interesting to extend these to the corresponding Julia sets as well. So whatever equidistribution result you can prove here, is there an analog of that in this setting as well? So there are really many directions this dictionary can be used for. And just let me end by saying that there are also ways to mate a Kleinian group and a polynomial. So what I mean is, instead of mating two polynomials or two groups, you could actually start with, for instance, this group and this polynomial and join them together on a single dynamical plane. And that has the potential to explain some similarities between them. And then you can ask various questions about those, and it sort of reaches out to neighboring fields in complex analysis and dynamics of correspondences and so on. So let me just end by saying that this dictionary, which has been known for 30 years and is still emerging, has a lot of promise. There are lots of directions that can be pursued here, and these are any new link between these two classes of objects, three-dimensional or not, is always quite exciting. Okay, let me end here. Thank you.
Thanks a lot for the wonderful talk. Now let's open the floor for questions.
All right, can I go first?
Sure.
Hi, Sabyasachi, this is Gautam.
Hi, I'm Gautam.
Could you, I actually have two related questions, but could you go back to the slide where you talked about the canonical biholomorphism between two Baire slices, please?
Right. Yeah, here.
Yeah. So, you talked about the natural biholomorphism between two Baire slices, and and then you talked about the analogous equivalence between polynomial parameter spaces, and you make a statement about these maps typically not extending continuously to their boundaries. And in framing the problem at the bottom of the slide, you seem to mention proofs about non-existence of continuous extension.
Right.
So my first question is, when you talk about the non-existence of a continuous extension, naively one would think in terms of some example where the natural biholomorphism doesn't extend continuously, but you talk about proving these things, and you said that the proofs in the two different settings are on fundamentally different planes at this point of time in the current state of the art.
Right.
So probably when you are talking about proving, you have some statement about most biholomorphisms don't extend continuously, right? So in what sense are you talking about the non-existence of continuous extensions? That's the first question. And then secondly, I mean, as an analyst, what is interesting is the existence of continuous extension to the boundary, regularity of boundary behavior. So what's so interesting in this situation where, in fact, what you want to prove is the non-existence of continuous extension?
Okay, yeah. So let me try to address the first question. So, honestly, I don't know what a unified framework would be, but the reason why, so first thing, I'm not asking for extensions or continuous or discontinuous extensions of arbitrary biholomorphisms. I'm talking about a natural biholomorphism. So I'm not talking about whether there is a biholomorphism between two sets, and these are higher dimensional parameter spaces, higher dimensional sets in some Cn. So I'm not asking if there is some biholomorphism that extends continuously. The biholomorphisms are dynamically defined. So
sure.
Yeah, and so sorry, I forgot your first question. But okay,
so are you saying that you talked about proofs of non-existence of continuous extensions? So is there some sort of, so if one is talking about a proof of this phenomenon, are you saying that predominantly for a predominant class of such biholomorphisms, or for a predominant class of dynamically constructed correspondences between polynomial parameter spaces, one notices that they are very irregular at infinity, very irregular at the boundary?
Yes, okay, right, yeah, that's right. That's what I mean. And actually, I mean a little more than that. I mean that one should also try to understand where it extends continuously and where it doesn't. And that relates to
I see.
So the mismatch, so both the proofs have a certain similarity, and that was this mismatch between algebraic and geometric limits sort of alludes to. What this means is that a sequence of maps can converge in coefficients to a limiting map, but that does not mean that the dynamics of this sequence of maps will converge to the dynamics of the limiting map. And that is the mismatch. Now, there are some known, it's known in the two worlds when these two limits differ. In most cases, it is actually known. And the conjecture is that discontinuity will only happen at the points where the limits actually do not agree. Everywhere else there is continuity. And if you know exactly where continuity holds, then as you said, it's more interesting to have a model. If you have discontinuity of the boundary extension, then that's not good, but maybe you can take a quotient by pinching, pinching the regions where discontinuity holds. And so you can look at a simplified object, a quotient of the actual complicated fractal where the biholomorphism does extend continuously. So just pinch all the regions where discontinuity holds. And that can be done if you have a complete answer or good control over regions where things are discontinuous.
All right, yeah. Okay, yeah, that automatically answers the second question as well.
Right.
Yeah. Thanks.
Right. Sure.
Any other questions?
Shubhojoy here. So yeah, so it's a very nice talk. I would like to ask about this compactness theorem that you mentioned. So as you know, in Thurston's theorem, I mean, in the limit you can sort of pinch measured lamination instead of, or a geodesic lamination instead of simple closed curves. So is there some kind of similar thing that's going on? Do you understand these limits in the polynomial case, the rational map case?
Right. So first, let me disappoint you a little bit, because we are talking about reflection groups. Here, the only things that so every degeneration is actually geometrically finite.
I see. Oh, okay. I see.
Because
okay.
you took, for instance, the thing I drew here, yeah. So this is, say, a reflection group, and you have a surface. So you have a surface. The surface has two sides. The point is, the two sides of the surfaces of the surface are naturally identified by an involution, which is the reflection. So whatever quasi-conformal deformation that you can do in order to stay in the world of reflection groups, it has to be symmetric. So curves that can be pinched are precisely those that are invariant under this anti-holomorphic involution, the front and the back. So that severely constrains the class of curves that you can actually pinch. So here it's just these kind of curves that you can pinch. So, right, so that means
I see.
Everything is geometrically finite, which is what allows us to which is what allows us to study the compactness of the corresponding hyperbolic component in the rational case. What you are asking is a really difficult question in general, whether there's an analog of double limit theorem or compactness for hyperbolic components in general. It's known in very few cases. And there are very few examples where it's known that deformation spaces of rational maps are bounded. I think the single biggest open conjecture is that, I think it's a conjecture by Macmillan, that so the classical Thurston's compactness theorem tells you that if you have a Sierpinski carpet limit set, then the deformation space is compact. There are also Julia sets that are homeomorphic to Sierpinski carpet, but it is still not known if the deformation spaces of these maps these rational maps are bounded. So somehow it's fundamentally more difficult than the group world because of the critical points in some sense.
Okay, thanks.
Sure.
Thank the speaker. I don't know how it goes in virtual things, but maybe I can clap. So yeah.